So this week and the next Tuesday, we're expected to finish the machine learning module because this is a module that many of you have already taken. So I'm just trying to review some key concepts. And I hope that you have gone through the complementary slackness after our lecture last Thursday and understood why those Lagrange multipliers or dual variables in the support vector machines formulation were zero if, or non-zero if and only if the corresponding primal constraints are not active, are active. So those multivariable, multipliers and dual variables will be non-zero only when the primal constraints are active. Those are support vectors because each primal constraint is corresponding to a training example, right? If that constraint is active, then that example is a support vector. Okay, so today and Thursday, we're going to talk about classification and regression. Two key concepts are about evaluating classifiers, integrating heterogeneous data today. Then on Thursday, we're going to talk about regression and bias variance trade-off and how you can be guided by under such principles to regularize the model complexity for the optimal trade-off. And next Tuesday, we're going to wrap up the machine learning module with some very practical knowledge about how do you diagnose your machine learning models. Okay, so then we'll finish the machine learning module and advance to the deep learning module. Okay? Any questions so far? Okay, so let's see where we are. Previously, we talked about support vector machine for binary classification, which can be extended in optimization formulation very easily to address, for instance, the soft margins versus the hard margins, right? And you can also address multi-class classification versus binary in this formulation. You can also change classification to regression in its formulation. So it's a very flexible formulation. And thanks to the fact that the training examples only enter the dual formulation through the inner products or the kernels, and the optimal solution also only, right, relies on the kernels between the support vectors and your X. Right? Due to that reason, support vector machines is a kernel method which can be easily extended, right, from the linear inner product kind of kernel to nonlinear, right, kernels. So, and you can go beyond this feature space into a higher dimensional kernel space, right? And we talked about the fact that this is a simple quadratic programming which can be solved analytically, right? And then there's an article that probably gave you some historical context about why there was a time that support vector machine completely beat the earlier neural networks. Hope you enjoyed that. So today I'm going to review first quickly. I'm going to talk about classification, but it's more than that. How do we evaluate classifiers? So it's just a quick review, but then I would spend more time talking about how do you integrate heterogeneous data. Don't forget that our motivating example is protein function prediction, right? And we'll use that example to show you how to integrate heterogeneous data and the theoretical ideas behind them. So let's talk about how do you evaluate classifiers. So how do we evaluate classifiers? Anyone? So you train a machine learning model, in this case, for instance, a binary classifier. How do you evaluate your classifier? You all know. you're going to look at the true positives, false positives. So in other words, you're going to have to look at a confusion matrix and then do some statistics, right? So very good. Anything else?
Depends upon a problem. So if we want to solve a problem where we need to decrease false positive and we don't get for true negative, then we'll validate based on that. So basically we'll need some extra samples. You can say validation or testing samples, and we'll validate performance of the model.
So you're saying that depending on the problem and the data characteristics as well as the desired performance, you may favor one assessment versus the other. And you also mentioned validation. We'll talk about that at the end as well. So yes, so as we said before, right, you're going to evaluate with validation set or the development set. So the first one is, just like Nami said, is a confusion matrix or the contingency table, right? So what you do is you first split your data into positives or negatives based on the actual class, right? Then you also further split them from the second axis, that is the predicted class. Then you basically split all the training example or validation set into 4 quadrants, right? And these quadrants are corresponding to true positives, false positive, and so on. When it's a true positive, it means that the actual class is positive and you predict it to be positive. It is positive and it's a true positive. False positive means that it's predicted to be a positive, but the actual class is negative, okay? So the positives and negatives are talking about the prediction, and the true or false is about the agreement between the prediction and the actual class, okay? Based on these values, right, because you split the cardinality, you split the data set into 4 quadrants, so the cardinality, so you have 4 cardinalities, so these 4 subsets, and you can use these cardinalities and calculate a lot of things, right? So the true positive rate is called the recall. It's also called sensitivity, which is out of everything that's predicted to be positive, what portion is true positive. In other words, it's looking at the first row, right? You're looking at the block of true positive divided by the true positive plus false positives, okay? So that's a sensitivity. False positive rate is a false alarm rate. That's the number of false positives divided by the number of negatives. So the false positive divided by this second column, right? Oh, wait a second. When I said the true positive, did I say the first row? I apologize for that. It's a first column, okay? So the true positives divided by everything that is actually positive. Okay, so out of everything that's positive, including the false positives that you made the wrong prediction, what percentage is true positive? Okay, so the sensitivity, this is the false alarm rate, false positive rate. So accuracy is this diagonals, true positives plus true negatives divided by the total. So this could be depending on whether your positive and the negatives are balanced or not, this accuracy could be largely dominated by the positive or the negative class, right? So then there is a balanced accuracy, right? And precision is out of everything that's predicted to be positive, right? So that's the first column. That's the first row. Everything that's predicted to be positive, right? So that includes true positives and false positives. And among them, what portion is true positive? And then F-score is blending precision and recall together, and specificity is 1 minus the false positive rate, right? Right, so in other words, it is true negatives divided by the negatives, okay? So there are all kinds of measures, right? So you can choose one of them, right? So what is the limitation of these measures? Do we need anything else to assess your classifier? What other assessment have you seen in classification? And when would you use those assessments? Of course, there's other kind of measures to summarize, right? MCC, for instance, right? You can summarize these performances based on these measures. Is there anything else? You must have used the ROC curve, right? Receiver operating characteristic curves. So when do you use them? So the receiver operating characteristic curve is 1 minus specificity or false positive rate versus sensitivity, which is the true positive rate. So the fact that you have more than one point in this two-dimensional space is because your classifier could have different thresholds, right? So depending on the classifier predicted values, above or below this moving threshold, you could have different points, right? Let's look at this case. This point is 0, 0. So the true positive rate is 0 and the false positive rate is 0. What scenario is this? When would you have this? True positive rate is 0 and the false positive rate is also 0. When would that happen? Huh? No data? False positive rate equal to 0. Let's look at false positive rate. Is the number of false positives divided by negatives. So that means false positive equal to 0. That means true negatives equal to negatives, right? In the meantime, what? The true positive rate is 0. So that means this is 0, right? And false negatives equals to positives. That means for all the negatives, you predict them to be negatives. So the false negative rate is 0. But in the meantime, for all the positives, you also predict them to be negatives, right? So your predictions are focused in the second row. They are either true negatives or false negatives. In other words, you predict everything to be negative, okay? Similarly, if you are here, then the sensitivity equal to 1, so the true positive equal to positive. But the false positive rate equals to 1 as well, so that means what? That means all the negatives were predicted to be positives as well, right? So in this case, we have everything to be predicted to be positives, right? And what about this point? This point is false positive equal to rate 0 and true positive equal to 1. What does it mean? True positive equal to 1, that means out of all the positives, they are indeed all predicted to be positives. But in the meantime, the false positive rate equal to 0, that means out of all the negatives, none of them were mistakenly classified either. So that means perfectly classified, right? All positives are predicted to be true positives and all negatives are predicted. So that is a perfect prediction. So if you change the threshold of your classifier, you may end up having multiple points. For instance, you reach A and you reach B and you reach this point, right? So in this case, we may never get this perfect point, right? But this tells you that this is a ROC curve that basically tells you the threshold independent behavior of your classifier. Then if you can if you want to quantify this one, you can just look at the area under the curve. Apparently, the highest area under the curve is this perfect condition, that's 1. The lowest is totally opposite, that's 0. So it's between 0 and 1, the higher the better, okay? Okay, so how do you do that? As I said, again, you should know this very well, that for instance, if you have this class distribution, and you also have the model or classifier predicted score, right? So of course, if your threshold is fixed, like 0.5, then you can calculate given a fixed number of sensitivity or specificity, right? But if your threshold is changing, then you end up having a ROC curve, right? Like this, right? So again, it always passes 0, 0, and 1, 1, right? But then you see, as we go above, right, for instance, we can start from this side, right, where we predict everything to be positive, right? Then we start, so that's like the threshold is minus infinity, right? So everything is predicted to be positive, excuse me. So that's where we are. Then we gradually increase the threshold from minus infinity to something, and the first time that threshold change will result in a sensitivity or specificity change is when that threshold reaches the smallest score. Is that right? Right? Like 0.1, right? So once you are above 0.1, you can say that, well, everything, right? Everything is positive except number 20, because that's below, right, 0.1. So in that case, it is negative. So in this case, we predicted all the positives correctly because they are all above 0.1. So the true positive rate is 1. But the false, and then we keep going and reach 0.3, right? Then we finally reached a wrong classification. When you say that the threshold is slightly above 0.3, then we mistakenly think that number 19 is a negative, right? Because the higher the score, we think it's positive. So in that case, your false negative rate is going to be 0.9 here, right? So you're going to keep dropping. And why do you have this staircase kind of shape? Why? Why do we have this staircase shape? Because we have finite samples, right? Again, these sensitivity specificity only change when your threshold hits one of these score values, isn't it? If you have infinite amount of samples, then or the scores are very close to each other, right? Like a fluid distribution or continuum distribution, then your curve will be smoother and smoother, isn't it? Right? But anyway, you can calculate the area under the curve. So this is just a review. I believe that you have learned this before. But can anyone tell me, why do we want to bother to do this? Use a threshold independent ROC curve and quantify the classifier's performance using the area under the curve. Why do we bother to do this? Why aren't we content with just a fixed point for a given threshold? Why do we need the curve? Anyone? Or when do we need the curve? Any ideas? Okay, so as I said, that the ROC curve gives you the ability to rank the two classes, right? So there's no doubt of that, and it's going through all the thresholds and see this distribution and look at the curve and the area under the curve, right? So the benefit of looking at the ROC curve is that it's not that sensitive to the class distributions, okay? So you may look at different accuracy or sensitivity level for different data sets simply because they have different class distributions, right? So then, right? So that's one issue you don't want to be biased about, right? So that's one reason that you'd like to use these kind of curves, okay? Besides, and then saying that, oh, this is a single value performance between 0 and 1, very convenient, there's also a very deep reason of utilizing this area under the curve. It's not something heuristic. It actually equals to the probability that a classifier will rank a randomly chosen positive instance higher than a randomly chosen negative instance. So this is a chance that a randomly chosen positive is going to be ranked higher than a randomly chosen negative. So if it's 1, it's really ideal. If it's 0, it's very bad. And a random predictor, like a flip coin, is going to give you 0.5, right? So that corresponds to this dashed line exactly. So this is a random classifier whose area under the curve is 0.5, which exactly gives half chance to rank the random positive above the random negative. Okay, so there's a deep reason of using this area under the curve. It's not heuristic, okay? Besides the area under the ROC curve, there's also the area under the precision recall curve, okay? So sometimes the ROC curve can still be misleading, especially for imbalanced classification with a severe skew and a few examples of the minority classes, right? Sometimes we have very small percentage in the data set that belongs to the positive. For instance, if you look at the protein-protein interactions, right? So if you look at the residues in protein 1 and the residues in protein 2, right? And then we have m times n pairs, right? If you classify those m times n pairs into positives, interacting pairs, versus negatives, non-interacting pairs, the interacting pairs are minority, isn't it? That's like less than 1%, isn't it? So in those cases, we have a severe skew, and the ROC AUC can be extremely misleading. You can get ROC AUC like above 90% very easily, to be honest. And in those cases, so I put some codes here. You can read them into more details, right? So in those cases, the precision recall curves are recommended for the highly skewed domains, okay? So in those cases, your x-axis is the recall. Like the, sensitivity is 1 minus specificity, the y-axis was the recall, okay? But your y-axis here is the precision. That's a true positive divided by everything that's predicted to be positive, okay? So in this case, the perfect point is here at 1 and 1. Precision equal to 1 and recall equal to 1. That means, recall equal to 1 means out of all the positives, they are all correctly predicted to be positive. And then precision equal to 1 means out of everything that's predicted to be positives, they are all positives, right? So that's perfect, okay? But of course, in reality, your model might be more like this, okay? It will always pass this 0, 1 and 1, 0, okay? And in this case, what's a random classifier like? In this case, the random classifier will have a flat line with a constant precision, right? And this precision equals to the minority positive class percentage, okay? If it's balanced, then this level will be 0.5, okay? So that's the control you compare to. It's no longer you're comparing to 0.5 anymore. Sometimes you could have area under the precision recall curve extremely small, like 0.01, but you have to compare to the baseline, which could be 1 out of a million, okay? So you have to use these numbers in their context, okay? All right. Any questions so far? Okay, after reviewing what metrics are used, just as you said that you have learned before that, now that we have learned each classifier, like the W in the linear classifier, or learned from the training set, we can evaluate the performance over the validation or the test set, right? But before doing that, there are still so-called hyperparameters to choose. For instance, if you're using the Gaussian kernel in the support vector machine, there's a sigma there. That is not a parameter, but usually treated as a hyperparameter, okay? So, in the neural networks, the number of layers, the number of neurons, those are like hyperparameters, right? So for those kind of hyperparameters, their optimization or gradients are difficult, right? So there's a reason that they are treated as hyperparameters. But even in this case, sigma is continuous. You still treat it as hyperparameters because they're in nature different from the parameters. So there is a question that remains is how do we optimize these hyperparameters, right? As you usually do is that you do like a nested loop, right? In the outer loop, you optimize the hyperparameters, and then for each, in the inner loop, for each hyperparameter combination, you train the model to optimize the parameters using the gradient-based algorithms, right? So one way to optimize the hyperparameter is using the validation set and do the k-fold cross-validation, right? So as a reminder, you just randomly split your training set into training and validation set into equal k partitions. K minus one of them will be used as training, and one fold will be used as the validation set. And you can keep doing this, and in total you have k ways to do that, right? So if it's 10-fold cross-validation, you can just repeat this process of training 10 times and validating 10 times, right? Okay, then for each value of a parameter, you have to average the performance in all rounds, right? Of a hyperparameter, I'm sorry about that, right? So, for instance, in each round, you can use AURC, AUPRC, we have talked about before, right? And then you can average them over the 10, right? And then that is the average performance for that hyperparameter combination choice, okay? So this is a very typical method, k-fold cross-validation. Again, I recommend you to take the course Pattern Recognition from Dr. Braganetto, who actually talk a lot about the small sample issue when in the training machine learning. So in those cases, k-fold cross-validation could be a very biased and non-optimal way to choose the hyperparameters, okay?